In the previous video, we worked example problems on limits of series, or just analyzing infinite series. So we're given an infinite series, and we analyze it to see if it's convergent or divergent. And if it's convergent, then what does it converge to? And we started off, we were given some series, and we just evaluated the a sub n at like 20 points, and then we evaluated the partial sum at like 20 points, graphed it, and just based on the graph of the points, analyzed it to see if, does the sequence of the series converge? Does the series itself, the S sub n, seem to converge? And so that gave us some good insights into analyzing series. And then from there, we were given we went to other types of problems where we were given a geometric series. We were told that it was a geometric series, and we wanted to analyze that to see if it was convergent or divergent. And if it was convergent, then we found what the infinite sum was, because with a geometric series, that's a special kind of series that mathematicians were able to figure out they could get the actual S sub n formula. And how you get the S sub n formula for a geometric series, that's what we saw in the video from the algebra playlist that's included in this playlist. You get the S sub n formula, you take the limit as n goes to infinity, you get the infinite sum formula. Okay, and so now we're going to continue with more example problems from this section. We were introduced to infinite series, and we're analyzing them for convergence or divergence. And we're going to start off with problems where we're just given a series. But we're not told if it's geometric, or we're not told anything about it. We're just given a series, and we want to analyze if it's convergent or divergent. Okay. So is this series here, and it doesn't tell us if this is an infinite series, but the fact that they're asking is it convergent or divergent, then that implies that we're talking about an infinite series. We can see it has a start point. And then since we're being asked about convergence or divergence, then we know they're talking about analyzing as the number of terms in this sum goes to infinity. Okay, so how do we approach this? What did we learn about convergence or divergence of series? Not a special type of series, just a series in general. Well, the main thing that we learned was that any series is like married to a corresponding sequence. So you have a sequence, a formula for a sequence. Let's say you can come up with a formula. Okay, and then the corresponding series for that sequence is you put that sequence into a summation formula. You switch the subscript to I, and so you're going from i's 1 to n. This is the partial sum, because you're going from you're summing the first n terms, but if you take the limit as n goes to infinity of this, then you have the infinite series. So before, this was called, you would call this like S sub n, and then this, they just call it S. This is the infinite sum. Okay, so where we can start is, let's see if we can get this A sub n here. All right, so it looks to me like the A sub n is, we've got the denominator of these fractions is a arithmetic sequence. So, and that starts at 3. So we'll say that we're starting at n is equal to 1. So our sequence in series are going to start at n is equal to 1. So in that case, what we do is we say that this is going to be 3 plus the common difference is 3 times, let me write this bigger. Okay, 3 plus the common difference times n minus 1. So when n is equal to 1, that's the first term, we just get 3. When n is equal to 2, you get 3 plus 3. When n is equal to 3, you get 3 plus 6. Okay, now we can simplify this. 3 plus 3n minus 3. So it's just 3n. Okay, and so that is we can write it like this. I guess what you would say is if you just want to put the S sub n, the partial sum, you wouldn't put this plus dot 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 at the end, but if you want to do the infinite sum, you'd put the plus dot dot dot. I mean, however you want to do it. Okay, so that's the A sub n. All right, so when it came to analyzing the convergence or divergence of an infinite series, what were some of the things we talked about? Well, the main theorem was that if a series is going to be divergent, so okay, we can write out the actual series. The infinite series would be the limit okay, if a series is going to be convergent, then the corresponding A sub n of the series needs to converge, and not just converge, but converge to 0. Okay, now before we could go down that path of analyzing that, but if we look, we can simplify this summation. We can take out the 1/3 from the summation, right? We could do that with summations, but then we can also take the 1/3 out of the limit as well. So okay, and I did this because what is this? This infinite sum with the A sub n 1 over n, that's the harmonic series. And we analyze this in the textbook. This is divergent. This is one of those cases where the actual sequence formula, the A sub n, if you take the limit as n approaches infinity of A sub n, it actually converges to 0. But remember, that doesn't guarantee that the corresponding series is convergent. It's like it's the only fact is the other way around. If a series is convergent, then that means the A sub n has to converge to 0. But the opposite way isn't necessarily true. It's not like if you find out that the A sub n of a series is convergent to 0, that means the series is going to be convergent. And this is one of those cases where it doesn't work out that way. So this is divergent. And we can look, if we want to be more specific about the divergence, we can look and see that it's not oscillating. It's all, you're adding all positive numbers. So this is going to diverge to infinity. Okay, so there's the A sub n. We can start by just, let's take the limit as n approaches infinity of the A sub n. Let's see if the sequence corresponding to this series is convergent or divergent. Because if it doesn't converge to 0, then we've gotten our answer. We know it's divergent. So okay, so this is equal to the limit. All right, so we divide the numerator and denominator by n. Okay, so as n approaches infinity, this goes to 1, this goes to -2, so -1/2. Okay, so this sequence is convergent, but it doesn't converge to 0. So that means we know that this is divergent. But now let's see if we can be more specific about this divergence. So what we can do is let's write out the first 5 terms of the series here. So, all right, when n is equal to 1, you've got 3 over -1, so -3. And then when n is equal to 2, you've got 4 over -3. So, okay. -4/3. So this should be minus again. When n is equal to 3, you've got 5. And then, is that right? Yeah, so -1. 5 over -5. And then 4, you've got 6 over 7, and then when n is equal to 5, you've got 7 over 9. Okay, so the S sub n is minus 3. Then minus 3 minus 4/3 is, that's minus 9/3 minus 4/3. Okay, minus 13/3 minus 1. So minus 13/3 minus 3 over 3 is minus 16/3. Minus 16/3 minus 6/7. Let me get the calculator out here. So minus 16/3 minus 6/7 minus 130 over 21. And then that minus 7/9 minus 439 over 63. So I'm assuming that this should be bigger than minus 6.9, and then this is minus 6.19, and then 16/3. So I mean, I probably want to do more terms, but it looks like this is going to negative infinity. I probably want to do more terms to verify, but that's what it looks like it's heading towards. Okay, here, this might be a geometric sequence. We don't know. So let's see if we can rearrange this and see if it perhaps is a geometric sequence. So we've got a sub n is equal to okay, so this is 3 times 3 to the n over 4 to the n. This is 3 times 3/4 to the n. Okay, but if we want to put it into that form where it's to the n minus 1 power, and then that's a nice form because then the coefficient is the first term. We would say, yeah, this is a geometric sequence or geometric series because it's a common ratio, right? We can tell from here that this is a geometric series because each time you're just raising the power on this common ratio here. So, okay, but so we see R is going to be 3/4. So geometric series R is 3/4. But what is the first term? So when n is equal to 1, what is this? Okay, it's 3 times, so yeah, A1 is 3 times 3/4, 9/4. So what we can do is we can write this as 9/4 times 3/4 to the n minus 1. And this is that form that in the previous example problem video that the theorem is the geometric sequence kind of summary of the properties of the geometric series is based off of, because again, you could use this formula even with n starting at 1. You can use this formula. That's fine, but this is kind of nice because you can see the first term and you can see the common ratio, and that's what the S sub n and the S formula, the infinite sum and the partial sum formula, the inputs are the first term and the common ratio. Okay, so all right, but the absolute value of R is less than 1. It's 3/4. So this series is convergent. It's a geometric series. What does it converge to? Well, this is what we worked on the previous example problem video. A geometric series converges to the first term divided by 1 minus R, assuming that the absolute value of R is less than 1. So this is 1 minus 3/4 and then 9/4. So 1 minus 3/4 is minus 1/4. Okay, so or no, 1 minus 3/4 is positive 1/4. So this converges, and the infinite sum is equal to 9. Okay, so let's just, I'm not sure if this is a geometric sequence or what potentially this is. As far as if this is convergent, what we've learned so far from the textbook is there's only two situations that they showed us where if we have an infinite series that's convergent, that we can actually find what it converges to. That would be for the geometric series, and then also if it's like a telescoping series situation. Okay, but let's just start with what we know. Here's this a sub n. Let's just take the limit let's get the limit of the sequence. Let's see if the sequence is convergent or divergent. Okay, so let me rewrite this. It's easier to see. Okay, so as n goes to infinity, this goes to infinity. 1 over infinity is 0, goes to 0. So this goes to 1/4. Okay, and so this is divergent. We know for sure if a series is going to be convergent, then the sequence that corresponds to that series has to converge to 0. It doesn't. It converges to 1/4. And so if we were trying to get some information about this divergence, then what you can think about, since this converges to 1/4, then then the series as n goes to infinity, you're going to be adding 1/4 every time. When you're off at infinity, each successive term you're adding 1/4, 1/4, 1/4, 1/4, because that's what the series is, right? You're adding the terms of the sequence. And so you can see why a sequence must converge to 0 for the series to converge. Because if it doesn't converge to 0, then if it converges to something else, well, then you're going to be adding those terms. So this is going to converge to infinity. In fact, if we come back here, we could have used that same analysis here. Since this converges to -1/2, you're going to be adding, whenever you get off to infinity, whenever you go way down the series, you're going to be adding -1/2 every time, because the sequence converges to -1/2. So you're constantly just off at infinity. You're doing -1/2, -1/2, -1/2, -1/2, -1/2. So with that, we could have just seen that this is going to converge to negative infinity. Not converge, it's going to diverge to negative infinity. And same idea. And same idea here. This is going to diverge to infinity. Okay, this is a geometric series, because it's a common ratio. You're multiplying each. You can tell clearly you're multiplying each term of the underlying sequence of this series by sine of 100. For every as you go to the next term, each term is being multiplied by sine of 100. Okay, so all right. Well, what is sine of 100? Minus 0.506. This is R. Okay, and so the absolute value of R is less than 1. So this is going to converge. Okay, so, and we can actually find the actual what it converges to, because this is a sequence, a geometric series. All right, now we need to, it's not in that form with the k minus 1 where we can read off what the first term is. The first term is not going to be 1, because this is when the first term is going to be when k is equal to 1. The first term is sine of 100. So this is equal to, I mean, we don't have to write this out. I mean, yeah, I'm not going to write it out. Okay, the infinite sum is equal to the first term over 1 minus r. The first term we can see when k is equal to 1, the first term is sine of 100 over 1 minus sine of 100. And that's it. Okay, so just looking at this, I mean, only thing I can think to do is, I don't see like a potential geometric series, or maybe even like the potential telescoping series where we could separate this into two separate terms, and but then those terms potentially cancel each other out in the infinite sum. But okay, we can always start with what we know. So the a sub n is natural log okay, does this sequence converge or diverge? We learned how to analyze sequences for convergence or divergence in the previous section. So what we can do is we can take the limit. We can look at this as like this is a function applied to an a sub n, where this is the a sub n inside the natural log. And since the natural log is going to be only going to have continuity issues at 0 or something negative, but there's no problem there. This is never going to be 0 or negative. So we can say, what is the limit? What is, if this was its own sequence, the argument inside the natural log, does that sequence converge or diverge? And if it does converge, what does it converge to? This is equal to, all right, so divide the numerator and denominator by n squared. Okay. So then goes to infinity, this goes to 1, this goes to 2. So, okay, and so that means that this sequence here, the limit of this sequence is the natural log of this, since this function is continuous at what this converges to. So the limit of a sub n is equal to natural log of 1/2, which is minus natural log of 2. Okay, and so what does that tell us? That tells us that since the sequence here doesn't converge to 0, this is going to diverge. And what does it diverge to? Well, let me make sure that this is actually a negative number. Logarithms are kind of confusing. Yeah, so it's going to diverge to negative infinity, because the sequence, as n goes to infinity, it's just repeating values extremely close to this. So you're going to be just adding negative numbers. All right, so we've got this arc tangent of n. That's the sequence formula. So let's just go ahead and see if that sequence converges or diverges. Limit as n approaches infinity of arc tangent of n, and this should go to like pi over 4. Pi over 2. Okay, so this is divergent, because the sequence underlying this series doesn't converge to 0. And this is going to go specifically diverge to infinity, because you're adding positive numbers. You're adding pi over something very close to pi over 2. When you're off at infinity, you're just adding something very close to pi over 2 over and over and over and over again.